and he's one of the organizers of the workshop.
I have everything, yeah. Okay, so I want to talk about very new work, for us new, so it's something we did in the last half year in our group, and so the number of junior people, Arjan Salaf, Anand Subramoni, Guillaume Belek, and then also Robert Legenstein, professor who talked already before then. And we have, a few weeks ago, we have put a preprint on arXiv which sketches some of the results. About 2/3 of what I will discuss is already in this preprint. And so I want to introduce a new version of spiky neural networks, which we call LSNNs. I will have a short look at their computation capabilities, and then I come back to a theme which Matt Botvinnik introduced yesterday, namely learning to learn. And so I will discuss not only learning to learn from rewards, but also learning to learn from a teacher. And then a summary. So we have been working on networks of spiky neurons in Graz for quite some time. But over the years, I got the impression maybe these networks of spiky neurons are a little bit dumb, at least if you compare them with artificial neural networks, particularly recurrent artificial neural networks. As you know, these networks have been shown to be really powerful. And I'm talking here, I might talk only about really recurrent neural networks. And so this was shown in a landmark paper from the Hinton Group 2013, that really substantial jump in speech recognition capability can be achieved with what they call deep recurrent neural networks, and then also the state of the art of speech translation, for example, uses recurrent neural networks. But if you take a closer look, these are not networks of the usual type of recurrent sigmoidal neurons, but they're of LSTM units then. And so I think at the moment, if one looks at literature and artificial recurrent neural networks, almost all of them, if they're really doing something remarkable, they have LSTM units or some variation of these then. And so a network of spiky neurons, this has been lacking. And this may be one of the reasons why one wasn't able to demonstrate similar computational capabilities for these networks of spiky neurons. So just a micro reminder of what these LSTM units are. So they were introduced by Hochreiter and Schmidhuber about 21 years ago. And I think roughly the idea is you want to have in a recurrent neural network something like a register in a computer where you put something and then it stays unperturbed until you want it then. And so this is actually something trivial, but in recurrent neural networks it's difficult to achieve because the dynamics is working on this in the recurrent neural networks, and all the units are kind of changing typically all the time then. And so this allows you to give you some desirable stability, temporal stability within a recurrent neural network. And so here you have therefore a so-called memory cell, and you can put in there a bit or number, and it stays there at the same value until you decide to change it. You let some input in, or there's a forget gate which kind of allows you to raise it, or there's also you can create an output out of the content of this memory cell then. And so all these other auxiliary gates, then these are regular type sigmoidal gates. They have weights then, and when you train LSTM networks and you train all these weights of these auxiliary gates, then, and when one looks at the state-of-the-art results and computations with LSTM networks, these are actually not very large networks. A few hundred of these LSTM units are typically already achieving really remarkable results then. So there's also simply a technical reason from the perspective of optimization or learning why these are good then, because if you want to train a network, a recurrent neural network through backpropagation through time, then you have to virtually unroll this recurrent parts, assuming these hidden neurons are recurrently connected. Now to do backpropagation, you create a clone of the same neuron set here for each time step of the computation then. And then all the connections run from one time step to the next time step. There's no connection within a time step. So therefore, you virtually kind of replace this recurrent neural network by a feed-forward neural network, which is as deep as the number of time steps you're considering here then. And so then when you do backprop for such a network, you do really backprop in this then deep feed-forward neural networks there. And so therefore, if you have here now, for example, a unit here which is connected to itself with a weight W, then here you encounter products of this W with the power, the depth of this, which can be 1,000 or so if there are 1,000 time steps then. And so typically, then if W is larger than 1, this explodes. If W is less than 1, this vanishes. And so this creates this well-known problem of exploding or vanishing gradients here. And so this is something which is avoided by these LSTM units, because here the key point is that this basically has weight 1 to itself, because it remains there unless you want to change it. So just having here the self-connection with weight 1 basically allows you for these units to avoid this problem with this exploding or vanishing gradients then. So we found out that we can apparently capture a central part of this capability with something extremely simple then, which goes really back to neurophysiology. So if you, for example, look at the brain atlas of the Allen Institute, they report among many fingerprints of really biological neurons, the so-called adaptation index. And so they measure here, when you, in the case you give to the neurons simply a step current then for a certain amount of time, then actually most neurons don't just fire then at a constant rate, as simple neural models, leak integrated fire neurons would predict. But typically, many of them will have a kind of a rate which slows down then. And so therefore, this measure here looks at the interspike interval n+1 and compares it with the preceding interspike interval. So therefore, for example, if this quotient has if they're double this interspike interval, this quotient here has the value 1/3 then, right? So this is 2 times as large as this one, and so 1/3 here is the value of this, if though the interspike intervals doubled here from spike to spike then. And in this Allen Institute database, you see then they have measured these adaptation indices, which are measured like this. And so this case of the doubling of interspike interval would be here at the level of 0.3 then. And you see here there are quite a number of neurons also which have an even higher adaptation index. So these are simply profiles of, I think, 150 or so neurons actually from the human cortex, which happen to be in their database. And it gives us an idea. So these are the neurons here, which have this adaptation index 0, which have no adaptation then. And so there is a large fraction of them, maybe 50 or 60%. And then you see other neurons which have the spread of this adaptation time constants. So if one wants to model these neurons, actually in literature, most of the standard modeling approaches like Ishikowitz neurons and adaptive exponential fire neurons can be adjusted to this. We wanted to have here extremely simple model for this, just this adaptation effect. And so therefore, we have here a firing threshold for the neuron J, call it BJ, like the bias of the neuron J, which consists of a constant value and then something Bj of t, which is time dependent. And so each time when this neuron fires, so then this set J is the spike train, binary spike train of this same neuron J. Whenever it fires, this component is non-zero, and otherwise alpha J is something between 0 and 1. Otherwise, this decays then. So therefore, whenever this neuron fires, maybe few spikes, this goes up, and then it decays then if there's no firing, and then if there's a firing, it goes up again, and so on then. So it's just an extremely simple model for an adapting neuron then. And it turns out that if one includes this adapting neurons in this network of spiking neurons, then one has nice functionalities. In particular also, I want to point out here from the technical perspective, one can actually also apply backpropagation through time to this network of spiking neurons then. So this is actually something which has been known now for a few years, that backpropagation through time works quite well for networks of spiking neurons. So this was from the Bengio group, and this was this IBM group. And they have proposed a very simple solution. If you have a spike, then you have here step function, which basically decides whether there will be postsynaptic potential in other neurons or not. And so here, you don't have a derivative here. But if you simply use here a pseudo derivative, which goes up and down, then it turns out that backpropagation through time works quite well then. We had here made one change to the usual way. It turns out it's actually good to have the amplitude of the pseudo derivative less than 1. So this is a technical aspect. But then in principle, it turns out that one can apply this backpropagation through time also quite well, even in the presence of this adaptive firing threshold, because this is a similar effect as for the LSTM units. If this neuron has a raised firing threshold, so it doesn't fire much, so therefore you have fewer of this kind of discontinuous steps, which cause always a little bit of a kind of an error in the backpropagating error. And then if the neuron is not firing, you just have here the smooth equations then, and so there you can really quite precisely compute the backpropagating error. So therefore this gives then the basis for looking at what we call now LSNNs, where L stands for something longer in time. It's really suitable for doing computations on a larger time scales also. And these networks consist then of a population of regular spiking neurons which are non-adapting, and another neurons, population of neurons which are adapting then, and both gets inputs and both gets output then. So this, introducing these adaptive neurons was one step to increase the computational power of network of spiking neurons. The other step was not to use now a kind of naive architecture like complete connectivity or random connectivity like in a liquid, but rather optimize this architecture for a range of computational tasks. Then this turns out to be really essential. So for optimizing now this architecture together with optimizing the weights or so, we use these methods that Robert had sketched this morning then. And then we come up rather than networks which here kind of pseudo-randomly connected. You can hardly see this. One gets then, one can in principle program into this rewiring algorithm any desired sparseness of connectivity, and then you get particular kind of connectivity connection probabilities for these 3 populations of internal processing neurons then. So one kind of standard test for the computational power of LSTM-like networks, artificial networks, is to do MNIST, but in a really weird way then, because you have here an MNIST handwritten digit, but you present it 1 pixel at a time then. So you simply have a schedule where this pixel first goes to the first row, then to the second row, and so on. And the gray value, when it hits then a non-white pixel, then the gray value of this pixel is then kind of given as input to the spiking network, in our case here, in the form of a population rate then. So you have here population, in this case, of 80 neurons then, and the firing probability of these encodes the gray value of this pixel. So if we see, for example, here now this is now the input over time, over 800 milliseconds, so 1 pixel each millisecond. And so then you just first have this empty rows, then you hit here the row where there are few non-white pixels. Then again, there's this white part, and then a little bit later you again go through here. And so this is now the thicker part here. And so this is now the way how this hand region 3 is encoded and presented to the network as simply as a temporal pattern then. Is this clear? So this is not something now we invented. This is a standard benchmark task. And actually, one can argue it's a really stupid way of giving hand region digits to a neural network. But on the other hand, if you really look at how the brain actually gets visual input, it's actually also maybe captures something which is interesting, because even if you look at a static image, then you're doing a scan, then right now your fixation point moves around then. So in the end, even a static image is presented to a brain as a time series then, right? So it's not a stereotypical time series, but it's a kind of picture-dependent, attention-dependent time series. But the brain also gets visual input, even for static images, as a time series. So this is a fact. But here at the moment, we were just interested in exploring the computational power of these networks there. And so this is now here the adaptive neurons here. These are these excitatory and inhibitory neural networks. And so these are now this firing threshold. You see they're kind of moving up then as soon as there's some activity in some hard to understand way. So the output here was encoded by a softmax here then, and one sees here the kind of the time course of these different outputs. So there are 9 different possible digits then, and so we saw here initially this network considered various options what it might see. So initially thought maybe it saw a 2, which makes sense. As long as you see only this part here, it looks like a 2. Later it thought maybe it's a 6 when it got to see this then. And then only at the very end, we cue this network to give now a final output. Then it actually converged here to the 3 then. So if one takes the statistics of performance of different networks, so this is shown here then, the test accuracy. And so here the red ones are artificial neural networks. And so if you don't have LSTM units, it's not very impressive performance. LSTM networks get without so much fine-tuning here to 95 or 96 then. And now the interesting point is that recurrent spiking neural networks are even worse than just vanilla artificial recurrent networks. But now the LSNN version gets even with a kind of a stereotypical architecture to high value. And if we include this rewiring then into the learning algorithm, then we can reach here about the same performance level as LSTM units. And so this was for me something which I found surprising. I haven't seen so far any way of approaching the computing capability of LSTM networks with spiking neurons. So then one other aspect where LSTM networks really play a prominent role is virtually all recent work in machine learning on learning to learn really considered in the inner loop LSTM networks then. Also the work of which Matt Botvinnik reported used these LSTM units in the inner loop then. And so therefore we wondered to what extent now we can apply similar learning to learn paradigms to networks of spiking neurons then. And I was always interested in this learning to learn aspect, because I have the feeling that when we are training an artificial neural network, say on ImageNet, we are doing something very different from what biology does to enabling a brain to recognize images then. Because there's apparently quite a bit of innate knowledge from evolution in the design of the visual system in the brain. And then before the brain gets to see ImageNet data set, it has learned lots of things. Like as a baby, it started maybe recognizing the face of the mother and maybe some other important things. And slowly, it has been expanding over time to learn more and more complex visual recognition tasks then. So it was not really one learning phase where all the visual object recognition capability was built up, but it was a stepwise process, a curriculum. And I think it would be very nice if you could understand the advantages of these mechanisms, and then also use them to both to enhance our understanding of learning in biological neural networks, but also use them to create better learning algorithms for artificial spike neural networks, say in some spike-based hardware. And then I think most of you may have heard of these ideas. Josh Tenenbaum and others in cognitive science have pointed out that to make use of this transfer knowledge or innate knowledge, probably one has to, these networks need to have a certain also abstract knowledge level then. And I find it's really exciting research problem, how networks, artificial neural networks or also spike neural networks can actually express abstract knowledge. How do you program abstract knowledge into a network? How can it apply this abstract knowledge to any concrete computational task then? And so I think our hope is that by looking at this learning to learn paradigm, we can make progress in our understanding of these problems for networks of spiking neurons. And so there has been quite a bit of work on learning to learn, actually going back several decades. But I have not seen work so far applied to network of spiking neurons, and so we were curious to explore this. So before I show there some concrete results, I would just want to remind you of the theoretical framework here, that in principle, learning to learn means you have two learning algorithms working in parallel then, an outer loop, which is typically more an optimization algorithm, and you can think of this mimicking evolution there, and the inner loop, which mimics then the learning for the concrete current tasks then. And the standard setup is that you don't have a single learning task, but you have a large, in general, infinite family of learning tasks. So maybe think of all the possible learning tasks which a particular neural network is likely to encounter during its lifetime. This would be introduce such a family F of learning tasks. So roughly in this outer loop learning or optimization algorithm, you draw various tasks from this family. You let this network learn on this, evaluate its fitness, and then depending on this outcome, you adapt certain hyperparameters, which are controlled only by the upper loop. And so what these hyperparameters are, this is something which is up to the user of this model, so there is no canonical interpretation of this. A standard interpretation which Matt Botvinnik discussed, and also I will discuss, is actually here the really radical one, namely that all the synaptic weights of this network here are hyperparameters, so therefore they're controlled only by the outer loop. And when now this network gets a certain task C to learn, it cannot change its synaptic weights to learn this task C, then it has to use its kind of working memory in its dynamics there to really accumulate results then and provide the basis for decisions there. So here, for this outer loop optimization, so I don't have scruples here to apply backpropagation through time, because this is not claimed to be a biological optimization that we or I understand. Then I think more really evolution taking place here then. And so it would of course be nice to really model evolution, but I think the parameters which are controlled by gene regulation networks are quite opaque then, so I'm missing there really a nice formalization of this optimization task from the perspective of evolution in biology. But also one can in principle also use then gradient-free methods like evolution strategies, which seem also to work reasonably well then. And so there's also one technical remark for those who care about this backpropagation versions. Then when we use here backpropagation for the outer loop, then we give this algorithm access not only to the fitness, but also to the errors that it makes for a particular input for this learning task C then. So therefore, you can then this outer loop can change its hyperparameters to reduce the error that this network makes then. But this has to be done in a careful way, because it's not the goal of the hyperparameters to optimize fitness for any single learning task, right? It should, for any even unseen learning task from this family, it should optimize its fitness. And so therefore, typically, one simply implements this by accumulating backpropagating errors over several tasks C then before they're really applied then. So therefore you avoid this theta gets over specialized for particular C then, right? You try to capture changes in synaptic strengths or connections which are useful for generic subset of tasks from this family F then. So therefore here the testing in this learning to learn paradigm is structured different from the usual setup in machine learning. As you all know, in machine learning, you typically have one learning task, and for testing, you draw new samples from this learning task then. But here testing even draws a new learning task then, right? But still from the same family of learning tasks. And so then this was in the paper from Maass group 2 years ago. This was sketched then, and also in this more recent Nature Neuroscience paper, you can read this formalization. So this was just here my introduction to this. And so as I mentioned you have quite a bit of freedom in both defining the family F of tasks then, and also what the hyperparameters theta should be, which are controlled by the outer loop. And by playing around with different families and choice of hyperparameters, one can get quite a number of interesting new insights about spiking neural networks. And I just want to show you 2 examples for what achieves in this way then. But they only use this kind of default assumption that all the synaptic strengths and connections are controlled by the outer loop. They cannot be used for learning a particular task then. And so this is something actually I found quite inspiring also in particular in the work of Matt Botvinnik, because it has become such a standard in theoretical neuroscience that learning takes place through SCTP then. If you really look at the data in experimental neuroscience, I don't really see strong support for this then. So look, for example, at the work of Frump-Gossou, who has studied quite carefully how a particular synapse responds to pre- and postsynaptic pairing. You see each synapse has its own kind of will. Some of them don't change at all. Some of them go up. Some of them go down. And particularly, you have to repeat this pairing at least 10 times to see any change then. And typically, to see kind of significant weight change, you have to pair it 80 times or 100 times. And I don't really see the ground when I learn a certain task, how to open a bottle or so, that these 80 different pairings of the same pre- and post-synaptic firing in the same temporal distance takes place then. So I think that theoretical neuroscience possibly has run a little bit into kind of a blind alley where it really has focus on this assumption that SCTP is the most standard and most credible learning rule for neural networks in the brain. I don't see this then. And so therefore I find it quite convincing to also know these ideas that there are other temporal processes and adaptive processes in the brain which take place then, which are usually ignored in these types of studies. And so therefore here, in this case, when we now use adapting neurons, the adaptation or the firing thresholds would be the one which are really adapted and accumulate statistical knowledge from the current learning tasks then. And so this seems to work actually remarkably well then. And I think I see this only as a kind of a first trial balloon. In principle, there are dozens and more longer lasting temporal processes from the time scale from seconds to minutes and longer in biological neurons and synapses there. And I see this adapting firing threshold just as one kind of representative of this large set of mechanisms there which can serve here in a similar way then. And I want to discuss 2 demos, and one is very similar to the demo which Matt has discussed in their papers, and then I want to go back also to this Hochreiter paper which Matt Botvinnik also has mentioned then. So learning to learn from rewards, or meta reinforcement learning as they call this, is something where the fitness of this network consists of accumulating many rewards then. And so therefore one uses here in the outer loop advantage actor critic algorithm, which is a tuned version of policy gradient in combination with deep learning for optimizing fitness of the value function and the policy then. And so here, as also Matt had described, or the setup here, the n gets as input the current state. I think, yeah. So this is it gets as this is now this network, the spiking network now in this talk, in this inner loop here, and it gets the current state of the agent as input, the reward at the preceding time step, also the action at the preceding time step, and it outputs the a particular action and estimated value of this action in this state then. So we took a simplified version of a Maass navigation task, which Matt Botvinnik related to. So we didn't want to go into visual processing. So we have here just discrete two-dimensional grid of 4x5 cells then. And the rule was, in one corner there was always a goal then. And then the agent had 100 steps altogether to reach this goal as often as it wanted then, or could then. So whenever it had reached the goal, it was reset to a random other position in the maze then. And so initially, it didn't know anything about the organization of this or neighborhood relationship of the cells. So the current discrete position, the grid cell in which it was given in one hot encoding to the spiking neural networks. And it got a reward 1 each time it reached then this goal then. So this is now here, and so these are here the training episodes in the outer loop. And we see here, we go here to 150,000 episodes. So this is something also which I learned here. It's not enough to consider 1,000 or so training episodes for the outer loop and sees remarkable things happening in this range if one goes to a few 100,000 and the training episodes in the outer loop then. So here early on, when the network hadn't really acquired any useful knowledge about this task, then you see it was started here and it just randomly bumped into walls each time when it goes outside, and just by sheer luck it found here the goal then. But when it was set up here in a particular state, it still was cruising around. It didn't directly go here then. So therefore it got only few accumulated rewards. So this here measures for these networks how many rewards they are able to gather then within these 100 steps then. So this is 20 would be close to optimal if one thinks these are 5 steps just to go down here then. So after training, one sees actually this network of spiking neurons in the inner loop, just a few hundred, I think 200 or somewhat less spiking neurons is quite good then. So it started out here. It first looks whether the goal is in this corner, and then it looked into this corner. Then this was the first pass then to exploration. Then it was randomly reset to this one. So you see it goes on the shorted path to this corner. When it was again reset here, it goes straight to this corner. So one sees here that the spiking neural networks in the inner loop had learned something which is for a computer program, I think, not easy, but I have never seen this in a spiking neural network, because you see here, after learning, this network of spiking neurons has acquired really a clever exploration strategy, and then once it has found what the location of the goal is, it was able to apply this learned knowledge now in many different situations where it was randomly put into other situations. So it was exploiting this learned knowledge then. And also it was controlling now really behavior over quite a number of time steps then. So here one can also have an inner look now at the workings of this. So this was the untrained network after very few training. So it got a reward. Let's see. Yeah, so these are these inputs to the network. As I mentioned, it gets a state and the action. And here this is actually, I think, signaling it got no reward, 0 then. Only if it gets a reward. Now I think it gets here a 1 then. And so you see here the activity of these networks. We don't quite know. I can't see any pattern there. So now here is this trained network, which really has learned this task very well. So you see each time it gets a reward. Now this is marked here by this line then. And then it's put into random position and it moves straight to this goal that it has found then. And so you see here now certain patterns in the activity, and also now these firing thresholds are moving in a particular ways. and I don't understand how this network is doing this. And so this is something which I find interesting, that now we have now in our hands or in the computer spiking neural networks which can really perform tasks which I think we cannot construct, or I wouldn't be able to construct the spike neural network by hand to execute this task. And we don't even know how it really handles now this task, or how it uses now these firing thresholds to accumulate knowledge about maybe this one had remembered the location of the goal here. No, it was in the upper right corner, so, but we don't know this yet. So this is just something where we have now to start to explore then, or reverse engineer these circuits which are optimized for particular learning tasks. Here in this year, the task to learn to navigate in these mazes then. And also we get certain optimized architecture out of this optimization in the outer loop. Then we have to understand what aspects of this architecture are essential for this then. And I think the program is obviously to extract principles of the functioning of these networks and then put these principles by hand then into new neural networks and see whether they can learn then even faster there. So I think this is certainly unsatisfactory that we get these networks only constructed by external optimization processes. The goal is to really understand why they work after this extended optimization process and use then this recipe to build their networks in the end by hand then in a much more clever way then. But I think this is not unlike just the goals of experimental neuroscientists, right? You record from networks in the brain. The brain can do really very complex tasks. We don't really know how this exactly is happening. So I think that the main point was is, in some sense, that one can port quite a bit of the work of the Botvinnik group, also to networks of spiking neurons and exciter and inhibitor neurons, which is quite nice because if one then wants to relate the emergent activity and coding properties of the network to recordings from the brain, one can now, when one has exciter and inhibitor neurons, can compare this with firing of corresponding cells in the brain, whereas LSTM units doesn't have really a kind of activity which I would be able to relate immediately to brain networks because it really has different type of coding then. So I want to quickly also discuss here this learning to learn from a teacher. How much time do I have actually?
I think we started a bit late, so you have like 40 minutes now, so about 40 minutes.
So yeah, let's run quickly to this. I think this is something which is possibly a nice continuation of this discussion which you started yesterday, and Tim Limikrab described, namely the problem, how can biological neurons do something backprop-like then? And one sees here in yet another hypothesis how this could happen in biological networks of neurons there. So this is now something which is follows this inspiration of Hochreiter, where we, in principle now we want to kind of induce these spiking neural networks in the inner loop to be able to learn an input-output behavior from supervision there. So it gets, as each time step, it gets a new, in this case, two numbers between 0, -1 and 1 then, given in population coding. And it's supposed to give now the output of some unknown artificial neural networks for this input, x1 and x2 then. And so it has to make a guess then. Of course, in the beginning it has no idea what the output, but then at the next time step it gets the kind of the correct output then for the input at the preceding time step. So this delay of giving the target output one step later was introduced by Hochreiter simply to avoid cheating then, because if you give the input to this network and the target output to this network, and you now ask the network to make a prediction, of course it would simply copy this teacher given input and say this is now my prediction then, right? So by giving this correct value, the correct output always after this network has made a prediction, you avoid this trivial cheating then. But no, so you still, but it's still supervised learning insofar it gets all the information only with some time delay. And in principle, it could compute now the difference between the output it has given for a certain input and the target output, and can do with this error whatever it would want to do then. And the interesting aspect is that if one takes a closer look at this setup, it has now the freedom to really use a very large set of possible learning algorithms for solve this problem, where we would use backprop here now to apply this here. But you see here, the only way now this network can produce here outputs is using its internal activity dynamics. So there are only local kind of connections in this network, of course. By definition, only activity of neurons can be transmitted. There is no other way of doing backpropagation of errors. There's no separate transmission line really for errors in this network there. And only connections existing in the networks can be used. So therefore, the network is forced to use only its own dynamics there to do whatever it wants to do as replacement for backprop. On the other hand, earlier theoretical work had shown that, just in some sense it's trivial, that since this is in principle if this would be an artificial neural network, it could approximate a large number of possible learning rules then. So therefore the optimization of this network could in principle now pick out of this infinite reservoir of possible learning rules for such nonlinear artificial neural network any one which works best then. So this is now here just a quick demo before I come to the end of how this spiky neural network solves this learning task after training in the outer loop. So here you see this is always one time step. I think it was chosen here 20 millisecond long, where it gets two input numbers, x1 and x2 in population coding, and then always the target output value for the preceding time step. So therefore, this is here now a number of steps. So in 15 steps, it has 15 times going through this routine. It gets the input. It has to produce a guessed output. It gets the correct output then. So when measures here now the quality of its output, this network had, after 15 such steps, almost learned what this target network would be then. So basically, it had this replacement of backpropagation through time was now in place after these 15 steps then, which were in some sense non-trivial because it was always given random values as input, right? And so therefore, it could not just use a simple lookup table or so to find out what is now the target network then. And again, we have now a kind of reverse engineering problem. So from this time point on, this network has really captured some insight. It knew what was this unknown target artificial neural network, which it was supposed to emulate now in its input-output behavior. The question is where and how this insight is encoded there. So one sees here, these are the activity of adapting neurons. And I don't see really anything different from before then. But here, from this point on, the information about this target network must be in the network then. And we're starting now to try to reverse engineer what was this kind of learning algorithm which emerged then in this spiky network through this optimization process. And there's one hint that it's not like backprop because it has a certain Bayesian feature. So we simply made an experiment that during training we shown target networks with 4 different target networks with 4 different parameterizations here more often than the other random networks. And after then, when we tested this now, again on this kind of more often previously shown networks, it was converging much faster to a low error than for a new random network, a new random parameterization of this. So therefore, it had already some priors extracted from this long training phase then. So this is something which I have not seen in backpropagation networks. So therefore, apparently this network is now implementing some type of Bayesian algorithm there. So coming to the end, so I think that we are seeing now really a jump in the computing and learning capability of spiky neural networks, recurrent spiky neural networks, where they reach in some aspects the capabilities of LSTM networks. We don't know yet for more difficult tasks how far they can go and how well they compare with LSTM networks. So this is work for the next year. But also we see just practically deep learning has become now a tool for producing computationally powerful spike neural networks, and in particular recurrent neural networks. So one usually thinks deep learning is something which only deals with feed-forward networks, right? Here we're aiming at producing computationally powerful recurrent neural networks. And we see very well that deep learning method, just backpropagation through time, is a powerful tool to do this, right? And the link is obviously this unrolling of this recurrent network into a deep feed-forward network, just for the purpose of applying backpropagation here then. So then I think we see that this very nice relations which Matbot-Winning had sketched between their learning-to-learn results and brain data can now be carried out also on the level of neurophysiology, that we can now try to relate also emergent firing patterns in the network, which emerges through this optimization, which recordings from corresponding brain areas. One also aspect which I find interesting in here, that we set it up in a way where these networks, the spike networks, always had to come up very fast with an action or so in the reward-based learning task. So therefore, most of the computation really is carried out really with single spikes or spike patterns. It doesn't really fall back into a trivial computation with rate patterns. And I think this is something where we particularly need more kind of paradigms for how this can take place. Then it's very hard to construct by hand spike neural network, which really uses coding with single spikes. Particularly also this works also this results if we put noise into the network, and then it's particularly difficult to carry out powerful computation with single spikes then. Then we see also that if we wonder about how the brain learns nonlinear input-output behaviors, that is a whole new range of possible learning rules, not just variations of backprop, but also simply this learning algorithm which emerge through these optimization processes, which rely simply on dynamic processes within this network, which are there already in it anyway then. And so then I think I see a very nice convergent kind of joint activity with work in computational neuroscience in advancing the art of reverse engineering then. And I think here one has actually one advantage over experimental neuroscience, because we can carry out even more experiments with this network of spike neurons which are produced in silico. And on the other hand, we certainly make use of all these methods which have been developed already in neuroscience for the same reverse engineering tasks then. So this was all.
Correct me if I'm wrong, but you have been assuming that the neurons are deterministic. There is
you mentioned, I think, particularly we had tested this for this last experiment with this supervised learning. We had put noise in there, and it still worked then. So I think these networks cannot typically gain too much capability from being deterministic, because when they learn something, there's anyway kind of unpredictable which inputs come in there. So they have to be able to deal with non-deterministic scenarios. Otherwise, they couldn't deal with this learning task. But one certainly has to find out what is the level of noise, internal noise, which they can tolerate.
Yeah, I was wondering basically to what extent they are robust in their computation, given stochasticity in their operation.
Yeah.
So do you have any experiments that?
Yeah, as I mentioned, we have carried out this experiment also with noise in the network, so that for kind of simply just from this internal noise, if you see spike raster for the same inputs, it's hard to see that they're the same then, so kind of quite a bit of noise then. And certainly it's something one has to explore then, really new ways of doing noise, spike-based computation in noisy environment, in noisy network, right? So I think that we should expect that we get some new ideas from this approach.
So, Wolfgang, you learn these adaptation parameters in the adapting neurons via backpropagation through time?
So far not then. It's actually something we probably will do then. So far we have put them kind of little bit like inspired by this L Institute data, some spread of these time constants which are in the right range then.
So use the diversity of the time constants like what you saw.
Yeah, And it's not quite clear now. We have seen also kind of puzzling cases where we knew that working memory had to last for, say, 8 seconds in some of the tasks, which I didn't show. And we put in adaptation time constant, which acted on a faster time scale, and they will still be able to solve this fast then. So I think this is at the moment also something unknown to me, at least. What exactly is the optimal relation between this adaptation time constants and the working memory lengths which are required for a task then.
Actually, did you need the regular spiking neurons? Why did you still have a pool of regular?
I'm not sure whether we tested this to reduce them to 0. Yeah, I think it would be an interesting experiment. Yeah, but I would guess but you would need them. But because I think the problem is also if you use these adapting neurons for computation, in some sense they're rather unreliable computational units, right? Because if you use them a lot, like making them fire off, and suddenly they became very reluctant to fire again then, right? So, but it's certainly something to merge, to find out then, and possibly get at least hypotheses about the biological fact that you have both adapting and non-adapting neurons. And I have not actually seen also in neuroscience, maybe you know some kind of really ideas why adapting neurons are really increase the capabilities of the network. I think it has been usually viewed more as a nuisance than from the perspective of modeling. One suddenly sees here they really may gain quite a bit of computational power, namely essentially working memory capabilities for the network.
But I mean, it's the time scales, right? It just adds kind of memory units with longer time scales into your network. I guess that's the explanation, right?
Yeah, as I mentioned, sometimes we see also shorter time scales are sufficient. But then also I think it's something by hand I wouldn't be able to really construct the circuit with adapting neurons to really carry out a working memory task. And because you see it's tricky actually to read out the content of the working memory, right? Because they kind of express their memory by not firing, which is actually something which is smart probably from the perspective of energy efficiency, right? Rather than expressing memory by persistent firing, why not use non-firing then, right? But it's non-trivial to read it out then, because probably you have to try harder and harder until it fires in the end then. And then you, in this way, you can sample what the firing threshold was for this neuron then.
I'm thinking of the work of Rory Hassan at Princeton, who's proposed that there's a gradient across the neocortex, human neocortex, in terms of the time scales on which computation is focused, the kind of the width of the temporal window of integration. And so I'm wondering what the empirical data says about, this is the literature I don't know much about these kinds of adaptation effects. Is there evidence that, in fact, the kinds of adaptation effects you're building into your model here, the time constants on those vary across the cortex, like in the mouse or any other organism?
Yeah, we haven't looked at this data in the Allen Institute based on, so I guess now the data from human pyramidal cells are a little bit accidentally sampled then, because these were from clinical kind of applications there. And it's smallish then, but certainly this would be an interesting hypothesis to test, right? That in those areas where you think working memory it takes place, like prefrontal cortex, that you find longer adaptation time constant. And then actually also the other interesting time constant, right? We know that some neurons get more excitable after being active then, right? We also need to understand this. In the simulations, this turns out to be a more brittle process, because you can easily get the network overexcited if it has too much memory stored then, right? So, but it happens in the brain, but it probably is then controlled really by inhibitory processes which avoid this overboiling of the network activity. So we need to understand the use of these types of neurons for computations.
Maybe we should stop now and go to the break.
Yeah, and so we planned it for 4:30, so maybe we should not delay it until 4:40. And then also Fritz Sommer is then moderating this discussion. You want to say something now already, or?
Maybe one question to So we decided that we might actually stream the discussion. So would anyone anticipate to be less lively in the discussion if you would stream it? So if not, then I would say we stream it. Yeah, then I would say have coffee and then come it
for 40 then, yeah.
What is kind of missing of our current theories of brain computation?